All right. So welcome back. This is going to be my acid and base review for organic chemistry. Most of organic chemistry is based off of what you learn in inorganic chemistry with acid and bases. So what is an acid and what's a base, right? An acid is a compound that donates a proton, while the bases accept a proton. And as you can see by this little example here, since this hydrochloric acid is more acidic than the water will then take the hydrogen while the chlorine is left alone and stable, actually. So, well, as depicted here, there's a bonding arrow and a cleaving arrow. The bonding arrow shows that this oxygen is slowly going to bond towards this hydrogen, while this hydrogen's bond with the chlorine is going to be broken off. How come we need a bonding and a cleaving arrow? Well, with acid and bases, well, any compound really. For hydrogen, it is monovalent, meaning that it can only be bonded to one thing at a time. Same thing with the chlorine, it is both monovalent, therefore having 3 lone pairs and 1 bond pair. While water has 2 lone pairs and 2 bond pairs, bonding to 2 hydrogens and having 2 lone pairs. However, because of the fact that water is more basic than HCl, it's going to pull the hydrogen away, thus cleaving the HCl bond. When an atom loses a hydrogen, it gains a lone pair. What is a lone pair? As referenced before, lone pairs are the amount of valence electrons on an atom that are not shared with other atoms. So, for example, oxygen, well, to fill up the octet, it will bond to 2 hydrogens or 2 other atoms, but it will still have 2 pairs, 2 lone pairs to fill up the octet. If water loses a hydrogen, how many lone pairs does it have? So when water loses a hydrogen, it will become a hydroxide ion. Hydroxide actually, oxygen on a hydroxide will have 3 lone pairs because it lost the bond. So you can disregard this mechanism here for now. I'm going to show you what ARIO is. This is what organic chemists use to determine whether a compound will be an acid or a base within a reaction. There is also looking at pKa values on a set table, if you're really good at remembering all the pKa values. First one is atom. I just know it by electronegativity, but the more electronegative an atom is, the more stable it is when it donates a hydrogen. The closer you get to fluorine, the more electronegative the element is. So for example, the element below fluorine would be chlorine. Chlorine, HCl, as learned in inorganic chemistry, is a strong acid because it is very stable after losing a hydrogen. It's very electronegative after all. Other electronegative atoms would be oxygen. That's why it can act as an acid or a base, but in this scenario, we're talking about acidity, sulfur as well. And right below Cl would be bromine, which is also a very strong acid. Here's an example. So with NH2 minus, it is not very, I would consider it not very stable. Therefore, when we add HCl, it's automatically going to gravitate towards the hydrogen and pull it off the chlorine. Because ammonia is very stable and chlorine is very stable, this reaction is going to favor the product side right here. Resonance. After atom is R. And to determine resonance, we'll remove this, we'll take this example here, carboxylic acid, remove the hydrogen. And when you remove the hydrogen, the oxygen is going to have 3 lone pairs, right? Therefore, there's going to be a negative on that oxygen right there. Resonance is very important in terms of reactions, mechanisms, as well as determining acidity. So when there's a negative right here, it's actually going to delocalize throughout the entire compound, well, at least this portion of the compound, just to kind of pull out the electron density. But it's also to kind of delocalize the electron. So producing a pi bond with this oxygen here and the carbon in the middle, it's going to lose this bond right here with this other oxygen, referenced by these 2 arrows right here, making a double bond and breaking this pi bond off. And because of that, it's delocalized throughout these 2 oxygens here. Induction and hybridization. So induction, I, and O for orbital or hybridization are the last 2. In terms of determining REO, it would be atom being the most reference or most important, then resonance, then induction and hybridization. So induction is based on surrounding molecules. There's 2 oxygens here, and the reason why we have these 2 arrows here is because this electron density here is actually being pulled away towards these 2 oxygens. This makes this carbon right here a lot more acidic and more willing to donate the proton. On top of that, because of the fact that this carbon can actually make a double bond with this second carbon right here, it can actually resonate and kick this electron, the negative charge after donating the hydrogen, all the way up to these 2 oxygens. Orbitals. So the pKa value of a triple bond, like this one, is around 20, 25. Well, a double bond and a single bond, this one is, I believe, would be about around 40, 45. A single bond will be about 50. And as you know, from inorganic chemistry, the higher the pKa value, the more basic it is. So the lower the pKa, the more acidic it is. The hybridization of this sp orbital right here, these 2 sp carbons, provides more stability when donating this hydrogen. Actually, though, orbital is the least important, in my opinion, compared to atom and resonance when looking at acidity. Here's some practice. You can pause the video real quick. All right. I'm gonna swap to my iPad real quick just to do the problems with you guys. So the first problem was HNO3 plus H2O yields NO3 minus plus H3O plus. Let's see here. As you can see here, this nitrogen is gonna be bonded to 3 things, right? So that means that, oh, actually, it's actually gonna be bonded like this. So there's gonna be a positive and there's gonna be a negative right here. If this oxygen loses this hydrogen right here, it would then be able to resonate and bring this up. So in this term, this is the acid and water will be the base, right? I believe that this would be the one that is more so favored. All right. So in this instance here, we can see that there is an induction effect right here. And right here as well. And when this oxygen takes this hydrogen here, making this bond arrow and this cleaving arrow, we're going to get this right here, which is also an intermediate state because of the fact that the negative charge will not be very stable on the carbon. So we can actually resonate it up to this oxygen here, or the other one, whichever of your choice, to make this right here. Because of that, we have resonance, we have induction, right? Which is clearly a lot more acidic than KOH, which is a strong base. So therefore, it will favor this side. The product side again. Let's do the third problem. C6H5COOH plus ammonia to yield C6H5COO minus plus NH4 plus. Let's draw this out now. C6H5. All right. To determine this as a formula, you can actually use the HDI or the degrees on saturation. However, just for the point of this video, I'm gonna just draw out the compound. So C6H5, there's 6 carbons right here, 5 hydrogens bonded around the ring, right? And there's a COH, which is known as a carboxylic acid, plus nitrogen right here with 3 hydrogens, giving us this carboxylate right here. Always drawing your lone pairs just to make sure. So of course you can always just look at the pKa. Clearly this carboxylic acid is a lot more acidic than the ammonium. This ammonium is bonded to a nitrogen, which would mean that the ammonium is going to be less acidic because this is bonded to oxygen here. So let's zoom in right here real quick. Right. Comparing the acidity of these two compounds here, we can see that this hydrogen is bonded to this oxygen here. This one clearly has atom already, which proves that it's more acidic. This does not have atom. This does have resonance and induction as well, because of the fact that if you lose this hydrogen here, right, you can actually resonate this down and resonate this up, delocalizing that charge. And on top of that, there's that induction effect right there. Therefore, again, it favors the product side right here. All right. Let's see. Last problem. This is a phenol with CF3, which means that there's a trifluoride carbon at the bottom. Add in an ethoxide, potassium ethoxide right here. And as you know, anything that's bonded to the first row of the periodic table is ionic bond. This oxygen is going to take the hydrogen up top, which will kick off right here, making this right here. Oops. And ethanol. And there's going to be potassium right here hovering around this negative charge here. So, what do you guys think? So yeah, they both have ARIO, right? They both have that atom there. Both were bonded to an oxygen. Let's see. This does not have resonance though. Does this have resonance? Let's see. Let's draw it out. So we know that a phenyl looks like this, right? And there's gonna be that oxygen right there. This oxygen can resonate down and kick this bond up right there, making this intermediate state. Wow, that was bad. But it's okay. There you go. So we know that this has resonance. So it's already a lot more acidic than ethanol. But let's keep going for a bit. Do you know where the induction comes from for this? That's right. It will be the CF3 because of the electronegativity of the fluorine, right? However, because it's on the other side, it's very weak induction effect, but it still has that minor induction effect. I would say small I right there. All right. Let's go back to the slides here. Stop screen. And share screen again. I think that's it. All right.